You know, deep inside every single atom, there's a battle raging. A battle between the two most powerful forces in the entire universe. It's a story that, believe it or not, starts by complete accident in a dark drawer in Paris. And it ends with us learning how to create the power of stars, but also the power to level entire cities. So the big question is, how did we even begin to unlock the secrets of the atomic core? Let's get into it.
All right, so our story kicks off way back in 1896. There's this physicist, Henri Becquerel, and he is absolutely fascinated by the brand new discovery of X-rays. So he's experimenting with these things called uranium salts, basically rocks that have this weird property of glowing after they've been out in the sun. He thought, maybe there's a connection between that glow and these new mystery rays.
But then, of course, it's Paris, so a bunch of cloudy days completely messes up his experiment. He gets frustrated and just tosses the uranium salts and a photographic plate into a drawer to deal with later. I mean, without sunlight, nothing should happen, right? Well, when he finally gets around to developing that plate, he finds something impossible. The plate is totally fogged up, like it was blasted with light. This meant the uranium was giving off its own invisible, constant energy, with zero help from the sun. A total game changer. This discovery absolutely lit a fire under Marie and Pierre Curie. They jumped on this, isolating new elements that were even more powerful, things like radium. And what they found was just staggering. A tiny little gram of radium was like a miniature, endless furnace, just pouring out energy nonstop. This wasn't just weird. It seemed to fly in the face of the most fundamental law of physics we had, that you can't create energy out of thin air.
So this became the single biggest puzzle in science at the turn of the 20th century. I mean, think about it. If the laws of physics say matter and energy are conserved, then where in the world was all this impossible power coming from? Finding the answer to that question was going to completely rewrite our understanding of the universe.
Okay, to solve this mystery, we've got to shrink way, way down. I'm talking impossibly small. We're going right into the very heart of the atom, the nucleus, because that's where the real battle begins.
So the nucleus, right? It's this super tiny, incredibly dense core made of two kinds of particles, positively charged protons and neutral neutrons. But hang on a minute. Anyone who's taken a basic physics class knows that positive charges are supposed to push each other away, like magnets, violently. So how in the world are all those protons jammed together in that tiny space without the whole thing just exploding? Well, the answer is basically a cosmic tug of war. You've got two forces going head to head. On one side, you have the electromagnetic force doing exactly what we'd expect, trying to push all those positive protons apart. But fighting back is something way, way stronger, the strong nuclear force. It's about 100 times more powerful, but here's the catch. It only works over ridiculously short distances. Think of it like a cosmic superglue that only works when things are practically touching. So the stability of every single atom in the universe hangs on this delicate balance. As long as that superglue, the strong force, has a tighter grip than the electromagnetic force trying to push everything apart, the nucleus stays in one piece. But if that balance gets thrown off, well, that's when things get very interesting very fast. So what happens when that balance finally breaks? Well, that's the origin of radioactivity. It's the exact thing Becquerel stumbled upon by accident. You can think of it as an atom's desperate attempt to get back to a stable, balanced state. Now, this problem really shows up in the biggest, heaviest atoms in the universe. As a nucleus gets packed with more and more protons, it starts to get, well, bloated. The protons on opposite sides are now too far apart for that short-range strong force to keep a good grip on all of them. And at that point, the long-range electromagnetic repulsion starts to win the tug-of-war, making the whole nucleus dangerously unstable.
So an unstable nucleus has three main ways to shed that extra energy and kind of calm down. First, it can spit out an alpha particle, which is really just a chunk of 2 protons and 2 neutrons. Or it can go through beta decay and shoot out a super high-energy electron. And finally, it can just release a blast of pure energy in the form of a gamma ray. And as you can see, each of these has a totally different ability to punch through stuff, from being stopped by a piece of paper to needing a thick slab of lead.
Let's look at beta decay for a second, because it's like a kind of nuclear alchemy. It's wild. So let's say a nucleus has too many neutrons for its own good. To fix this, one of those neutrons can just transform into a proton. Bam! But to keep the electrical charges all balanced out, it has to eject a tiny electron, that's the beta particle, at incredible speed. And in that one instant, the atom has literally changed what it is. It's become a completely different element on the periodic table. How cool is that?
Just figuring out that atoms could decay all by themselves was absolutely revolutionary. But the next leap, wow, it was even bigger. Scientists started asking, what if we don't have to wait? What if we could force them to break apart? What if we could tap into that incredible nuclear energy on command?
And that thinking led straight to the discovery of nuclear fission. The idea is actually pretty simple. You take a big, wobbly nucleus like uranium-235, and you just nudge it by hitting it with a single neutron. That's the last straw. The nucleus splits into two smaller atoms, releasing a huge burst of energy. But here's the really crucial part. It also releases more neutrons, and those neutrons can then fly off and split other uranium atoms, creating a self-sustaining, explosive chain reaction.
This terrifying new power was weaponized with just breathtaking speed. Right in the middle of World War II, the Manhattan Project took this theory and made it a reality. After the first successful test out in the New Mexico desert in July 1945, it was just weeks later that atomic bombs were used over Hiroshima and then Nagasaki, bringing the war to a very sudden and very horrifying end.
But it turns out splitting heavy atoms apart isn't the only way to get at their power. You can also do the complete opposite. It's called nuclear fusion. And with fusion, you take the lightest elements, things like hydrogen, and you use unbelievable amounts of heat and pressure to just squeeze them together until they merge. When they do, they form a heavier element, like helium, and this process unleashes even more energy than fission does.
And you know what? We don't have to look far to see the power of fusion. We literally see it every single day when we look up. Fusion is the engine that powers our sun and every other star in the sky. Deep down in the sun's core, there's a constant, relentless fusion reaction going on, turning hydrogen into helium and releasing all the light and heat that makes life on Earth possible.
So, to sum it up, we've got two different paths to nuclear power. There's fission, splitting big atoms. That's the tech we use in our nuclear power plants today, but the downside is that it creates long-lived radioactive waste. Then there's fusion, which joins light atoms together. That's the clean, powerful energy source of the stars. And, well, being able to harness that here on Earth, that's the holy grail. But trying to recreate the inside of a star is, you can imagine, one of the biggest scientific challenges we have ever faced.
But all this knowledge about the nucleus, it's about more than just power. It's unlocking some of the deepest secrets about the very fabric of matter itself, and it's pointing us toward entirely new frontiers in physics.
So it turns out there's this hidden pattern to what makes a nucleus stable. You know how electrons arrange themselves in these neat, stable shells around an atom? Well, it turns out protons and neutrons do the exact same thing inside the nucleus. And when these nuclear shells are perfectly full, that nucleus is exceptionally stable. The numbers of protons or neutrons that fill a shell are what physicists call magic numbers, like 8 or 20 or 50. If you get a nucleus like lead-208, which has a magic number of both protons and neutrons, it's called doubly magic, and it's one of the most stable things out there.
Okay, so this whole model makes a really incredible prediction. We know that as we create heavier and heavier elements in our labs, they usually get more and more unstable, right? They just vanish in tiny fractions of a second. But this theory suggests that if we could somehow create elements that have the next set of magic numbers, we might actually find pockets of surprising stability where we least expect it.
And this leads us to one of the great, epic quests of modern physics, the search for the island of stability. It's this theoretical region on the periodic table, way, way beyond any element that exists in nature. The idea is that super heavy atoms with these new magic numbers could exist there, and not just for a microsecond. We're talking minutes, maybe days, maybe even longer. Long enough for us to actually study them and figure out what they're like.
Now, actually reaching this island is pushing our technology to the absolute brink. It's a journey that could reveal even deeper truths about the fundamental forces that hold our universe together. So the final question really isn't just if we can ever get there, it's what strange new world of science will we find waiting for us if we do?